right, so this is our standard derivation. The other way of deriving this is by dimensional analysis. You just play with the variables and arrange them so that the units work out. What are the units for molar mass? The target units are going to be grams per mole. And so what you do is you just take all the variables and then just kind of place them until you get the right units, grams per mole. And then that tells you have the right equation. And so the density is going to be in grams per liter. R is liters, atmosphere per mole, Kelvin. T is Kelvin, P is atmospheres. So atmospheres cancel, Kelvin cancels, liters cancel, that gives us grams per mole. And so we could just play. If I have it upside down or if I have one in the wrong place, I'm not going to get the right units. And so I'll know if I have the right equation by looking at the units. Do the units work out? If they don't, then I have the equation wrong. And what I can do is if I have the units wrong, I could just, I must have put this one in the numerator, it belongs in the denominator. So if you do the memorization, you can always check your memory if it's correct. Well, anyway, the density of it is 2.32. So just put in 2.32 grams per liter. What is the molar mass? Okay, it's at STP. So the temperature is going to be 0 degrees C, which is 273 Kelvin. And the pressure is going to be, what is the pressure? Well, they're using the European one, so the pressure is going to be 1 bar. So this is 0.08206 liters times atmosphere per mole Kelvin. So we have to convert bar to atmospheres. So that's given the conversion factor. What atmosphere is equivalent to 1.01325 bar?
How do you know?
I don't know. Let me see. Let's see what they're doing. Yeah. They're doing it in bar also. So they have the R in atmospheres, and what they're doing is they're converting the pressure from atmospheres to bars. I don't know why they're doing this. This doesn't make sense. X that out. What's wrong? How do I know it's bar? Because STP can be 1 atmosphere, 0 degrees C, or 1 bar, 0 degrees C. Depends on who you talk to. What is the density of a sample of oxygen gas at a pressure of 1.40 atmospheres and a temperature of 49 degrees C? So what was the density equation? The density equation is, what is density? Density is mass over volume. Volume is equal to nRT, volume of gas, divided by P. And so we'll slip that in here. If you don't have it memorized, we can always derive it. And so it's equal to nRT over P. We'll invert and multiply. So this is going to be the mass times P divided by nRT. Do you see something in here that we can simplify further? And that is mass divided by moles is grams per mole. Grams per mole is the grams per liter is the density. Grams per mole is the molar mass. And so the density is equal to the molar mass times P divided by RT. Molar mass times P divided by RT. And so they're saying the effective air is a mixture. And so if I had a mole of air, it's going to weigh about 29 grams. So that's what they mean by effective. A mole of air has 6.022 times 10 to the 23rd molecules of air, which is a mixture. And so this is the molar mass of air, 29 grams per mole. Use this value to calculate the density of air at STP and at 20 degrees C. Well, probably the density, let's calculate the density. What would be more useful than this STP business is the density of air under normal conditions. So So what are normal conditions? And so let's calculate the density of air at 25 degrees C and 1 atmosphere. Did I already have you do that? No, I had you calculate the density of nitrogen, I think. So we're going to do air. And so the density of air is equal to molar mass of air times P over RT. And so the molar mass they're giving us is 29 grams per mole. The pressure, we're just going to use 1 atmosphere pressure, divided by R, 0.08206 liters times atmosphere per mole Kelvin, times T, 298 Kelvin, which is about room temperature. So room temperature and room pressure is what we have here. And so what is the density of air under these conditions? So it's going to be 29 divided by 0.08206 divided by 298. 1.185 grams of air per liter. And so the air in this room is about 1.19 grams per liter, 1.2 grams per liter. At STP, STP is colder. STP is colder, which means that the air expands or contracts as it gets cold. Contracts. You know, hot air expands, cold air contracts. So it's going to be a smaller volume. If it's a smaller volume, it's going to be more dense. But it's a lower pressure, but it's just a slightly lower pressure because atmospheres and bars are very close. So it's going to be slightly higher density, 1.3 grams per liter. At 20 degrees C and 751 torr, it's going to be somewhere in between. These two, because we're doing 25, it's 1.2. A 2.94 gram sample of an unknown gas is found to occupy a volume of 2.06 liters. So we have grams and liters, so we know the density. If we take the grams divided by the liters, we have the density. At a pressure of 1.16 atmospheres and temperature of 46 degrees C, what is the molar mass of the gas? Either that or we just use the original equation, because they give us the grams, they give us the, actually, what are we doing? Are they asking for the molar mass again? They're asking for the molar mass, which is the previous equation. But anyway, these are examples of density calculations. Let's see. And molar mass calculation. Molar mass. Yeah, this blue balloon is less dense. This is more dense in there. Now we have some molar volume calculations. So we did density, we did molar mass, now we have molar volume, the other specialty type calculation. Compare the molar volumes of helium and neon at 30 degrees C and 1.10 torr. So you have two choices for molar volume. For molar volume, you can memorize it. If you memorize it, you know, this is not a bad equation to memorize. Molar volume is equal to RT over P. You can always tell if your memorized equation is correct because of the units. You know, do the units work out? Oh shoot, this came unplugged. Do the units work out or not? So molar volume, RT over P, or we can derive it. What is the molar volume equal to? You have to know what the molar volume is equal to, you have to know what the density is equal to, you have to know what the molar mass is equal to in order to derive it. The molar volume is equal to volume over mole. And so if we look at PV equals nRT, this is another way to derive it. Another way to derive it is we want volume over moles. So volume divided by moles is equal to RT over P. So divide both sides by N, divide both sides by P. This is the molar volume equation. The other way we could derive this is the way I did it earlier. You know, there are lots of ways we can do these gas problems, algebra. And so the molar volume of helium and neon should be the same at the, molar volume does not depend on what the gas is. It could be neon, it could be hydrogen, it could be oxygen, it could be air. It's always the same. It only depends on the temperature and the pressure. So what is the molar volume of carbon dioxide? This is why the molar volume is a useful number to memorize at RT and P. And so we just plug in. You can calculate the molar volume for one of the most common things, one of the most common uses for molar volume is by stoichiometry. And so let's look at some stoichiometry problems here. But I'm going to twist these stoichiometry problems so that they're a little different. So for example, here it says find the STP volume. Do you think you're going to be doing this reaction at 0 degrees C? No. 0 degrees C is not realistic.